exclusively concentrate on thermal stresses, try to keep it within the topic. So primarily thermal stresses will be discussed today. So thermal stresses, they are a very important component of the discussion of strength of material because they affect the properties of the material adversely and sometimes may have undesirable consequences. So imagine that you have a bar AB as shown here. I'm going to take a look at the second case first. Let me get my pointer option. I'm going to take a look at the second case first here, the second picture, this picture right here. You have a cantilever beam AB. This is the part I am referring to. Cantilever beam AB. One side is actually connected. It's fixed at A and it is free to move at B. This could be a bar. This could be a strip. This could be a test coupon attached on one end and free on the other side. The material could be really any type of a metal or any type of material, but in this case, let's concentrate on metal. It could be really any kind of a metal. So any temperature change to AB would increase, well, or decrease depending on the temperature. It would result in a change in length or thermal strain. This is due to, if it is due to temperature change, we call it thermal strain. If there are, if this AB, if bar AB is free to move, expand, or contract, as you can see, there will be no stresses associated with the expansion. So this side is really free to move. There's no restraint here, so it can freely move. So as a result, we are going to only have the strain without having any type of stress. If I go from this picture, if I go up here to this picture that I'm showing up here, the first one on top, if I restrain both ends, then as a result, I'm going to have stresses due to the thermal strain. So please keep that in mind. If we restrain the elongation, we are going to have the stress. If we don't restrain the elongation, then if the supports are, if there's no support on both ends, or there is no support to stop it from any type of a elongation, then there will be no stresses. So that's a very important concept to keep that in mind when we talk about strength of material. So if we add the additional support and apply the principles of superposition, again, AB, the way it's shown up here, this is an indeterminate structure up to 2 degrees. The reason for that is because, actually up to 3 degrees. And the main reason for that is because we have 6 unknown here, 3 at A, 3 at B. So we have 3 reaction of the supports at A and 3 reactions of the support at B. And that put us to 6 unknown, and we only have 3 equations available. So that would bring us, give us 3 extra unknowns, and we need to solve that. In that case, we call it it's indeterminate to the 3rd degree or to 3 degrees. So because this is indeterminate, then we must use the principles of superposition to solve like that. Now, we're not going to solve this problem the way we do it to find the reaction to find the reaction of the support. Instead, we are going to pretty much take a look at how we can use this example to explain the thermal stresses. So the coefficient of thermal expansion, or thermal expansion coefficient alpha, you probably heard of that. That would pretty much is a quantity of the material. It's a coefficient, and it is different for different material, and that would pretty much determine how much a material would expand under increased temperature, or how much it would contract under a decreased temperature. We call it a coefficient of thermal expansion because we are dealing with increase in the temperature. So in order to find delta T, and delta T is the amount that the bar would elongate after we apply, after I increase the temperature by an amount delta T. So if that is if B is free to move. Also, if we restrain B, we restrain the support at B, there would be a reaction P. So simply I replace the structure up here by the length L under the application of delta T. When I increase the temperature of the system by a delta T, and there would be a reaction P at point B as a result. If I add A to B, if I add these two cases, and then I would achieve the structure up here as far as the thermal expansions are concerned. So the amount delta T, it relates by the length of the material multiplied by the thermal expansion coefficient, or coefficient of thermal expansion, multiplied by delta T. This is the amount of elongation that the bar AB would go through if its temperature would be increased by an amount delta T. The length of the bar is L, alpha is the coefficient of expansion, and delta T is the difference in temperature. Also, last time when we talked about strain in previous lectures, I would define strain as such, and we developed an equation in which the stress and the strain were related, and actually displacement or elongation was pretty much related to P, L, A, and E. Remember, E is the Young's modulus of elasticity, or simply modulus of elasticity. E is the cross-sectional area, L is the length of the member, and P is the force. And so having these two equations, delta T is due to thermal expansion, and delta P is due to force P. So the total delta, or total elongation of this member would simply, using the principles of superposition, is simply going to be delta T plus delta P. Now, we set that to 0 because we don't want to have any kind of elongation. As a result, we can calculate the reaction, the force P that is required to stop this expansion, or we can do different types of manipulation to come up with stresses as a result of thermal strain. So we are going to use these equations to be able to calculate the stresses as a result of thermal expansion, or delta T and alpha. So in this equation, remember that we need to have delta T, that's the temperature difference, and then we need to have the coefficient of thermal expansion, or thermal expansion coefficient, and we pretty much eliminated the length L. So that's important to realize. Let's do a small example, a thermal stress example. We have a bronze bar 3 meter long with a cross-sectional area of 320 square millimeter. This is again the cross-sectional area, so keep that in mind. It is placed between two rigid walls as shown in this figure, shown here. We call that P265. At a temperature of 20 degrees Celsius, the gap is 25 millimeters. So we already measured it. Find the temperature at which the compressive stress in the bar will be 35 MPa. Alpha is given, E is also given. A practical application of this problem is that we would like to limit the stresses that would be induced in this bar as a result of change in temperature. Again, we try to eliminate the stresses that are as a result of temperature due to compressive stresses. We did the design and this bronze bar, which is 3 meters long, is okay for strength. And we also check with the serviceability. That's also okay for serviceability in those two criteria. The last thing we check is we want to make sure that if this bronze bar is subjected to the temperature differences, we want to make sure that the stresses stay within the limit. So what we try to do is we try to find the temperature in this case. So again, we're using the same type of principles of superposition. There would be a total delta of the system. We're going to have the little delta, we're going to have capital delta. And for the small delta, that is the delta that would be from the reaction P, and there would also be a capital delta if the end of this bronze bar is free to move. Okay, so remember, if the end of this bar is free to move by an amount of delta, then that will be the total delta of the system. However, this bar is not free to move by an amount delta because at some point it's going to hit the wall, and there would be a reaction from the wall as this bar goes through expansion. So that amount, that little delta, is going to prevent further capital delta. So we need to pretty much calculate the total delta, which is delta, the little delta plus the capital, small delta plus the capital delta. That will be the total delta. So in order to do that, we are going to use the equation that I just showed you previously, and we are going to use this equation. This equation down here. We're going to use this equation. Okay, we set that to 0, and as you can see, delta L times delta T would be delta L over E plus 2.5 plus 2.5, and that is the millimeter of the delta. So here, this would be from that particular equation. And then down here, we're going to pretty much substitute the numbers that we have inside that equation. Delta would be 18 times 10 to the minus 6 multiplied by L. Again, L is in meter. We express it in millimeter. It's going to be 3,000 millimeter. And then the delta T, the temperature differences, or the difference in the temperature is the unknown. This is what we need to find out what that is. Okay, that's the question mark, a resemblance of a question mark. And on the right hand side of this equation, we have the little delta multiplied by 3,000 and so on. So this is the way we actually set up this equation. Okay, so the area is also given, and we place, as we mentioned, this bronze bar is placed between two rigid walls. So these walls are presumably are not allowed to move, and they cannot really move. So we again follow the calculation. E is 80,000 plus 2.5, which was, we use that up here in this particular problem. The capital delta was given 25 millimeter, as you can see up here. So we also use that 25 millimeter in the calculations. Temperature of 20 degrees Celsius. So from here, we're going to calculate delta T as 70.6 degrees Celsius. We already know that at a temperature of 20 degrees Celsius, the gap is 25 millimeter, and we're going to use that to our advantage and do our calculation, and then we subtract that 20 from 70.6 to see what will be the temperature at which the compressive stress in the bar would be 35 MPa. Remember, we use that 35 MPa here in this equation, and we followed with our calculation, as you can see. Something we need to note down here is that the units that we use, you want to make sure that gigapascal, the conversions between GPa and MPa and KPa, all those would be carried out correct. Okay, so that would be a good example of the real application of this in the real world problems. If you design a bronze bar as such, we already checked for the strength, so the member is okay under the application of loading or loads, and then we want to make sure that since it's going to be subject to extreme temperatures, we wanted to see that as a result of that, if the bar performs accordingly. In this case, up to 50 degrees Celsius, this bar could be heated up, and then we can make a decision as to use this or to increase the gap, or pretty much try to come up with other methods to solve this problem. That brings me to the end of today's topic. If you have any questions or comments, please feel free to contact me via the course website. I thank you for your attention.